Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the IB Physics HL May 2016 examination. This is a paper 2 problem. This is an older question, but it is going to be very helpful for your preparations for the May 2025 examinations and of course the examinations that come afterwards as well. Okay, let's get started. A company designs a spring system for loading ice blocks onto a truck. The ice block is placed in a holder H in front of the spring, and an electric motor compresses the spring by pushing H to the left, like so. When the spring is released, the ice block is accelerated towards the ramp ABC. So the ice block, for example, moves like so. When the spring is fully decompressed, the ice block loses contact with the spring at A. The mass of the ice block is 55 kilograms, so it moves something like that. It goes from here to there. Okay, so what I'm going to do, I'll just erase this and kind of make this diagram a bit better. So it loses contact and it eventually moves there. So like that, this motion. Okay, assume that the surface of the ramp is frictionless and that the masses of the spring and the holder are negligible compared to the mass of the ice block. The block arrives at C with a speed of 0.9 meters per second. Show that the elastic energy stored in the spring is 670 joules. Okay, well, to solve this problem, you can simply just use the idea of the conservation of energy. Okay, this concept is really helpful for most questions, and it is especially helpful in this question because that's what we're going to be solving it with. Conservation of energy. So we can use this problem for this question. Okay, think about it this way. When the spring is compressed, it stores a certain amount of energy. Okay, so at this point it has a certain amount of energy, and that energy is going to be equal to the energy the block has all the way at the top, because when the spring pushes the block like so, it transfers the energy that it has stored onto the block. So at this utmost position at point C, the block will have all the energy that the spring imparted onto it. Okay, so we can basically say the energy here is going to be equal to the energy here. So in other words, the elastic energy or the helical energy is going to be equal to this final energy at this utmost position. We can call that EF. So we can basically say that EH is going to be equal to EF. But rather than EF, what exactly is EF comprised of? It is comprised of a kinetic and a potential energy. So it's comprised of half mv square plus an mgh, because at this utmost position the block does have some velocity. It's not at rest. So it has a kinetic energy, but it also is at an elevation above the ground level. That means it also has a potential energy. So these two energies together, the total energy will be equal to the elastic energy. So let's put this in our calculator. So we know it is 0.5 times by 55, which was given to us, times by the velocity at this point C, which is 0.9 square, plus again the potential energy, now 55 times by 9.81 times by height 1.2 meters. So if I were to sum these two, kinetic energy and potential energy, together, what do I get? Let's see. 0.9 square 55 into 9.81 into 1.2. Add these two together, you get 669.74 joules, which obviously is almost equal to 670 joules. Hence this question has been complete. Now they're asking us to calculate the speed of the block at A. Now this is really simple. We use the same idea, conservation of energy, in A2. What does that exactly mean? Well, at A, the block is going to have a certain amount of energy. Okay, and that energy of course is going to be equal to half mv square. It's going to have only kinetic energy because the block is fully on the ground. Okay, as the block is fully on the ground and this is a frictionless ramp, no energy would have been lost. This essentially means that this kinetic energy at this position here is equal to the full elastic energy of the spring. We can basically say the kinetic energy at A is equal to the elastic energy, the helical energy, or whatever they call it. Because, and this is only true, this is true because frictionless. Because this ramp is frictionless, no energy will be lost. So the kinetic energy will be equal to the total energy of the spring. All of that energy, elastic energy, is imparted onto the block and is converted as a form of kinetic energy. And obviously, as the block starts moving up the ramp, this kinetic energy then starts converting into potential energy. So energy is always conserved. Okay, so use the same idea here. Okay, so kinetic energy half mv square must be equal to the total elastic energy, which we calculated it to be about 670 joules. So we can solve for V. So V is basically going to be equal to 2 times 670 over the mass of the block 55 the root of. So putting this on your calculator, let's see what we get. All I did there was some simple rearranging, nothing much. So you get about 4.94 meters per second, which is roughly, we can say, 4.9 meters per second for the sake of simplicity. Okay, now part B. Describe the motion of the block. So B1, from A to B with reference to Newton's first law. So using Newton's first law, we need to describe the motion from A to B. Well, we know it's a frictionless surface. And what does Newton's first law tell us? An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. So, as there are no external forces, or in this case friction forces, from A to B, so in this case external forces would just be friction. As there's no friction, object moves with a constant velocity. Okay, that's simple enough. Now I haven't really seen too many questions, latest questions asking us about Newton's first laws, but obviously it's good to know them and they're pretty simple to remember, so yeah, study them. From B to C with reference to Newton's second law. Well, Newton's second law is basically, we can just say the second law is basically just this expression right here. F is equal to ma. This is basically Newton's second law. That's what he derived. Okay, so as the block moves up the ramp, right, so for example like this, there's going to be a component, there's going to be a horizontal component acting on the block, a horizontal component of weight. So wait, let me draw it better and you can understand it better. So for instance, if the block moves like so, the block obviously has some weight and it has a normal force like that. So it has a horizontal force this way. You see, it has a horizontal force, sorry, the other way around. So if the block is moving this way, its weight, its horizontal component of weight is pulling it down. So there is obviously a deceleration. Okay, there is a deceleration, and therefore the object will slow down as it moves from B to C. As there is a component of weight acting down the slope, we can say there is deceleration, and obviously deceleration means object is slowing down. Okay, that's basically the motion from B to C. Now just to summarize it up, Newton's second law is basically F is equal to ma. Now if we just draw like the free body diagram on a ramp, we can see there is a horizontal component of weight that acts downwards, down against the motion of the block, and for this reason there's going to be a net deceleration, so negative acceleration. And because there's a negative acceleration, we'll find that there will be a force on the block, and because there's a force on the block, it will eventually slow down. Okay, on the axis, sketch a graph to show how the displacement of the block varies from A to C. Okay, so we know that basically from A to B there is no friction, so no loss in energy. So if there's no loss in energy, there is no acceleration, and if there's no acceleration, it's a constant velocity. So the velocity will look like so. The displacement with time will look like so. And just to know this, right, the slope of a displacement time graph is velocity. And so if there's a constant slope, that means it's a constant velocity. So from A to B, so that can be A, that can be B, there's a constant velocity. But we know from B to C, there is no longer a constant velocity because there is a deceleration due to the horizontal component of weight that acts downwards. So for this reason, the ending will look something like so, right? There will be the rate of change of velocity will decrease over time. There's a deceleration, and eventually the displacement line time graph will become mostly flat like so. Now, part D. The spring decompression takes 0.42 seconds. Determine the average force that the spring exerts on the block. Well, whenever there's a force and a time together in a equation, it usually hints towards using impulse. Impulse is basically just J is equal to F delta T, and that's given in your formula booklet. Well, J, the impulse, is nothing but a change in momentum, which is basically going to be the mass times the final velocity minus the initial velocity. And that's just the formula for a change in momentum. So, M Vf minus V initial over the change in time, which is 0.42, will give us F. Now putting everything inside our calculator, 55 times by, what's the final velocity? The final velocity, the moment it's released, is basically 4.9, and that over 0.42, which is the time for decompression, will give us the average value for the force. And putting this in our calculator, in 55 into 4.9 over 0.42, we get a value of about 640 newtons. Okay. Part E. The electric motor is connected to a source of potential difference 120 volts and draws a current of 6.8 amperes. The motor takes 0.5 seconds to compress the spring. Estimate the efficiency of the motor. Now, what is the equation for efficiency? Well, that's basically eta, which is efficiency, is equal to the power out over the power in times by 100. Okay, that's given in your formula booklet. Well, first let's calculate what is the power in. The power in is basically how much power am I supplying to this motor so that it can compress the spring. Well, we get 120 volts and 6.8 amperes. Now, in topic B, B5, we have a formula for power using amperes and voltage, and that's just IV. IV is equal to P, and that's basically 120 times by 6.8, and that will basically be 816 watts. That's the power input. Okay. All right. Now, what's the power output? Well, we can calculate that. The power output will basically be the, okay, what is power exactly? Before we do, what is power? Power is basically work over time. Now, upon fully compressing the spring, how much energy is stored? Well, we calculated that earlier. We said it was about 670 joules. So upon fully compressing the spring, about 670 joules is stored. So 670 joules over the time it takes to compress, 1.5. So what is that equal to? That's equal to 446.66. Now that's how much power it takes, is the output. That's the power output. So if I'm supplying 860 watts to actually compress the spring, the total power that's actually used by this, that's actually output by the spring, so making it do some action, is 446 watts. So if I were to divide 446, 6.66 over 816, what do we get? We get 54.74%. Okay, that comes out to be 54.74%. Okay, so just to sum up what I did, what is the power input? Well, I need to supply some energy into the motor for it to do some work, right? And that work is basically just a power. So okay, again, let me explain it again. I need to supply some energy into that motor for it to do some action. So it takes about 816 watts for it to do a certain action. But the actual output of that motor to actually do the action which I'm intending it to do is 446.66 watts. So if I supply 816 watts, the total output is only 446 watts. So this divided by that is about 54.74%. So some energy is lost in between. Okay. Now, finally, part F. On a particular day, the ice block experiences a frictional force because the section of the ramp A to B is not cleaned properly. The coefficient of dynamic friction between the ice blocks and the ramp AB is 0.03. The length of AB is 2 meters. Determine whether the ice block will be able to reach C. Okay, let's simply just draw this. Right, so let's just like make the surface rough. That's A, that's B, and that's C. And obviously that's a certain height up from the ground. Okay, so let's do it this way. How much energy do I need to have to be able to even reach C? Well, that's just the potential energy. The potential energy at C is the minimum amount of energy that I need to supply to ensure that my block at least reaches this point. So the potential energy at C will basically just be 55 into 9.81 into 1.2 that was given to us earlier. Basically, if I put this in the calculator, it's 647.5 joules. Okay, that's how much minimum energy I need to reach C. Now we need to find out what is the energy of this block at this point after it has moved from the spring. So the block will essentially move from A to B, but will lose some energy in this process because the surface of A to B has friction, so energy will be lost. We need to see if the energy lost is maybe not enough, that the energy lost will cause it not to reach point C. Okay, so let's do it this way. How will we find out? We need to basically equate the half mv square at this point right here. We need to show that half mv square is or is not equal to the potential energy. So that's is or is not equal to 647.5 joules. Now to do so, I need to find out what is the velocity at B. Now, how will I do so? Well, for this we can use our Stewart equations. We know that v square minus u square is equal to 2as. Now, a is the deceleration due to this friction. How can we find that? Well, the force of friction is basically equal to mu, the dynamic mu, times by n. And that's nothing but ma, right? Force is equal to ma. So we can say mu d, normal force is basically just mg, is equal to ma. So we can say that mu dg is equal to a. And that is going to be our acceleration, or in this case, the deceleration of this particular block. So we know the coefficient of friction, that's 0.03. 0.03 times by the acceleration, which is negative 9.81, will give us a. So a is basically equal to, let's see what, is equal to negative 0.2943 meters per second square. Okay, that's the deceleration. Fine. Now I need to solve for v square essentially. So how will I do that? Well, it's quite simple really, because we can say v square is going to be equal to u square plus 2as. Now we know what is u square. What is the initial velocity of this block? Well, the initial velocity at a which is right here, was 4.9 meters per second. We calculated that earlier. So V square is basically equal to 4.9 square plus 2 times negative 0.2943 times by the distance from A to B, which is 2. Now what is that equal to? What is V square actually equal to? Let's find out. Negative 0.2943, that's equal to 22.8328 meters. I mean, let's not give it a unit, okay? The V square is equal to this right here. Now if I substitute this into our kinetic energy, we can find out what is the energy at this point right here. So half times 55 into 22.8328. What is that equal to? That's equal to 627.902 joules. So basically, at this point right here, the block has 627.9 joules, but to get up here, it needs to have 647 joules. Now, as this block is clearly not going to gain energy during this motion, it won't ever be able to reach because it does not have the sufficient amount of energy to reach this point C. Therefore, we can say block does not reach C. Okay, thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.